So last time we saw this algorithm in green, which is proposed by Miller and Rabin. So input is number n is given in binary. First step, you just check whether n is a perfect power or not, or n is even, and then for a random a, what you will do is you will look at these UIs. Look at step 3. So UI is just a raised to n minus 1, a raised to n minus 1 by 2, dot dot a raised to m mod n, and you see whether this sequence has something unusual. Okay, so unusual would mean that 1 has a square root other than plus minus 1. That is what you check. It's a very fast algorithm. Now we were in the middle of this theorem, proof of this theorem, which says that if n has 2 or more distinct prime factors, then the number of bad a's, which will force the algorithm to say prime when in fact n is composite, is only 1/4, phi n by 4. Okay, so let us continue with the proof. So what we did, the way we started is we defined this b prime, which is a subgroup of Zn star, and b is a subset of b prime. This we had shown. So we will now focus on upper bounding the size of b prime. So we have shown that b is a subset, and we have shown this bound. We have shown this bound, which is related to basically GCD of m with p minus 1, and do this for all the primes that divide n. Okay, this is the size of b prime, and now look at the ratio of b prime over phi n. So this ratio came out to be smaller than product of half by p raised to e minus 1. So clearly if n has 3 prime factors or more, then the above is less than 2 times 1 over 8, which is 1 over 4. Okay, because half will be the contribution from every prime p. So you will get 1 by 4, so the proof will be over. Other good case is if there is a prime p dividing n such that p square divides n, which means e is at least 2 for this p, then the above fraction will be less than equal to twice. So this one contribution will already be half divided by 2, because p raised to e minus 1 will be at least p, which is at least 2, and the other will give you at least half, so which is again 1 by 4. Okay, so these are good cases. So the only case when this is not, in which case this exceeds 1 by 4, is so suppose n is equal to p times q for distinct primes. This is the only case that we have to analyze. So in this case, the ratio is half times GCD of p minus 1 by m. Let's write it like this, and q minus 1 m GCD divided by q minus 1 by 2 raised to L. Now this RHS exceeds 1 by 4, then what it means is that the product is exceeding 1 by 8. So see, you have to remember that the numerators divide the denominator here. So p minus 1 comma m GCD divides p minus 1 divided by 2 raised to L minus 1. This is because m is odd. Okay, so removing these two powers will not change the divisibility, and the symmetric thing for q minus 1 comma n m. So this means that either this fraction is 1 or it is smaller than half, right? So if both of them are less than equal to half, it's the same expression as before, but here it will be better to argue. So now look at these two fractions again. Either so each of these fractions is either 1 or it is smaller than half. If even one of these is less than equal to half, then this product will be less than equal to 1/4. So right hand side greater than 1 by 4 means the only possibility is that both of them are, each of them is 1. So p minus 1 m is p minus 1 2 raised to L, and q minus 1 m GCD is q minus 1 divided by 2 raised to L. That's the only possibility, only bad case to analyze. Okay. So let us call this p minus 1 by 2 raised to L p prime. So let p minus 1 be p prime and q minus 1 m be q prime. Both are odd. Because m is odd. So p minus 1 is 2 raised to L times p prime, and q minus 1 is 2 raised to L times q prime. And n is 2 raised to k m plus 1, but n is also p times q. So p is 1 plus 2 raised to L p prime, 1 plus 2 raised to L q prime, right? So this means that 2 raised to k m plus 1 is 1 plus 2 raised to L q prime mod p prime. So mod p prime, this first term p prime vanishes, and p prime is also odd, so which means that m is congruent to q prime mod p prime, but p prime by definition divides m. So m is actually 0. So which means that p prime divides q prime, and analogously q prime will divide p prime. So both of them will mean that P prime and Q prime are the same. Okay, which will mean if P prime and Q prime are same, then P and Q are same, which is a contradiction. Okay, so this contradiction means that B prime by phi n is 1 by 4 or less. Which implies that B is upper bounded by B prime, so it is also less than phi n by 4, which is much less than n by 4. Okay, so these bad A's which will fool the algorithm on a composite n output is prime, these are less than 1/4. So the error probability is less than 1/4. That is what we have shown. So Miller-Rabin test errs only when n is composite and error probability is less than 1/4. So it's a very good test. It's quadratic time and less than 25% error. Second simple observation is that MR test also can be de-randomized under GRH. Why is that? Well, this is just this Ankeny-Bach theorem under GRH. So we now know that B prime is a proper subgroup of Zn star thus from the GRH connection there exists an A between 1 and 2 log square n such that A is not in B prime. Thus the same A is not in B because B is a subset of B prime. So on a composite n, this A is a good certificate. Okay, so this A will force Miller-Rabin test to output composite, so it works. And all this is clearly deterministic polynomial time. So that finishes both Solovay-Strassen and Miller-Rabin test. Now, obviously, these are fundamental results. These are the best, one of the best industry grade algorithms to test whether a number is prime or not, where the number can be humongous. So the digits can be thousands and or more. Where is it used? So some of you may know that cryptography is a major consumer of number theory. Okay, so that we have already seen when we covered N-true crypto system, but that used lattices, right? N-true is a lattice-based, SVP problem-based, L-cube algorithm-based crypto system. But there is something even more elementary, simpler, which we will now exhibit, which is called the RSA crypto system. Currently, that is used more often over the internet, especially when you connect to your bank or when you use SSH, HTTPS, and so on. So example, when you use HTTPS or SSH or SFTP or digital signatures, etc. So what is this mechanism? Why will it need prime numbers? So let us do that. This is again a public key crypto system. It's also called asymmetric crypto system because for example, when you connect to your bank will tell you something, will publish the public key but will hide the private key, and that is enough for you to encrypt your message and send such that no adversary can break it. At the same time, bank can decrypt it. So both primality and the opposite of this, which is or the search version of primality is integer factoring. So both primality and integer factoring appear in a crypto system designed by Rivest, Shamir, and Adelman. In 1977. So again we will show the encryption decryption. Before that, the pre-processing is so pre-processing steps are carefully choose P and Q primes. These will be very large primes, and there will be also some other conditions which you need for the system to be secure. N will be a number, product of PQ, and phi n is the Euler-Toshan function, P minus 1 times Q minus 1. Also carefully choose an E between 1 to phi n. okay, and compute E inverse mod phi n. So, since E is co-prime to phi n, the inverse will exist. So, we chose PQ and we chose E, right? PQE are the three choices, and based on this your bank has public key and private key. So, they are as follows. Public key is E and N, private key is D, and of course P and Q. Okay, so bank will never tell anybody what is D and what is P and Q. The factorization is hidden. Public key is the number, and this E for exponentiation. So based on this, now we have encryption decryption. Encryption is, suppose M is the message that you want to send to the bank. View it as a binary string which you think of as a number, representing a number mod n, and then just exponentiate it by E. That's the ciphertext, and send the ciphertext. So this is called plain text or the message. This is the ciphertext. Decryption is on the ciphertext, bank will apply C to the D. And magically this will be message. Why? Why is this the original message is the question, right? So let's now prove that. So M is going to M to the E, which is going to M to the ED. What is ED? Remember, D is E inverse mod phi n. So this is 1 plus k times phi n for some integer k. What is M to the phi n mod n? This is 1. So this is M mod n. Okay, so prove this as an exercise, that M to the phi n is 1 mod n. So because of this, bank knows M. Now the question to ask is, an adversary listening in the middle, listening to you and the bank, the message you send, the C that you send to the bank. So adversary has E, N and C. So from that, so only knows E, N, C. Now using this, how will adversary find P and Q? That is the question of factoring in n. How will adversary find m? Well, that is the question of computing c to the 1 by e, right. These are the two natural attacks or algorithms adversary will try to find. Both are as conjectured to be hard. So what is open is given n e c is there an efficient way to compute well d, what is d? E inverse mod phi n is there an efficient way to compute d? That would immediately tell the adversary m using the decryption strategy, or c raised to 1 by e mod n, right, or just factor n. So any of these things, this or p. Could any of these be computed by the adversary efficiently? So till now there is no known way. It's an open question. It's a very important open question. So we can give names to these. This is called computing E inverse mod phi n not this one, c raised to 1 by e mod n. This question is called the RSA problem. And this is the factoring n problem. Okay, and this is the question of finding Fn. And it is known that this is equivalent to factoring. Okay, so basically the question is solve RSA problem, eth root finding, or factor n. It is not known whether the two are related. Yeah, so this is the state of the art. This is the best or most used crypto system on the internet. And already in the pre-processing step, you need good primes. Otherwise, this thing will not work. So finding primes reduces to testing them. So that is where primality testing enters. So primes p, this prime p is found by random sampling and primality testing. So you basically, if you want L digit prime P, you sample randomly an L digit number and then do Miller-Rabin test. With high probability all this will work and you will get a prime number. If it fails, you repeat, so on. Okay, this can be shown to work well. Okay, so we'll do one more thing in primality testing, and that is de-randomization. So now we will focus on deterministic polynomial time primality test. So this was an open question till 2002. In 2002 we solved it. So the first test was invented by Agarwal, Kayal and myself here in August 2002. Okay, so I will quickly go through this test. It will be much slower than the Miller-Rabin or Solovay-Strassen test, but it will really be deterministic and polynomial time, and it will not use GRH, unconditional result. Okay, so it's a major example of de-randomization. But it is not practical. Okay. So let us do the AKS primality test in the remaining time. So first we generalize the Fermat identity. To polynomials. So Fermat identity, remember, was for a prime n, a raised to n is a. What does it mean for polynomials? So we first make it slightly more general. So we say that n is prime if and only if x plus a to the n is x to the n plus a mod n. And what is x? X is not a number, it's a formal variable. In the polynomial ring. Mod n. So if x plus a to the n is x to the n plus a, then n is prime, and if n is prime, then this is true. A is just a number co-prime to n. You can even take it 1, take it to be 1. E is just a number in Z n star, x is a formal variable. This is very easy to prove once stated like this. So, in the forward direction, what you do, you write the binomial expansion x plus a to the n is n choose I, or a to the I x to the n minus I, and then you observe that mod n, since n is prime, mod n all these n choose i's are 0 except 2, the first and the last. So, I equal to 0, which is x to the n plus e to the n, which is again x to the n plus a because of Fermat's little theorem on numbers. Okay, so this is why x plus a to the n is x to the n plus a. In the converse, if this identity holds for some a, and for contradiction suppose n is composite, and say prime p divides it, then you can show that n choose p is not 0 mod n. This you can show simply by the definition of binomial n choose p. Essentially p is dividing in the denominator n times n minus 1 times n minus p plus 1, right. So, n won't be able to divide this number, and because of that x plus a to the n binomial expansion n choose p will survive. Okay. So, that finishes the contrapositive of the converse, hence the converse is done. So, if n is composite, this identity is violated. If n is prime, it holds. Okay, so this is a very good criterion, unlike Fermat's little theorem. Right, a raised to n equal to a, we knew, even if it is true for all a, it doesn't mean n is prime because of Carmichael numbers, but here indeed it is a criterion for primality. Now, can it be used in practice? The problem is x plus a to the n has n plus 1 terms. N plus 1 is huge when n is huge. So, it is not really practical at this point. So, computation of x plus a to the n mod n is infeasible as it involves n plus 1 terms. N plus 1 is more than 2 raised to log n. Exponentially many terms are there, so you cannot really compute all of them. So, the first breakthrough idea is compute an approximation of this instead of the whole thing. So, instead compute x plus a to the n mod n comma qx for low degree q. So q is not very high degree, and how do you compute x plus a to the n? It still has many terms. Well, you can now use repeated squaring. Since you don't want the whole expansion of x plus a to the n, but you only want the remainder, you can compute this by repeated squaring. So by repeated squaring mod n comma q, it takes time. So you will be doing squaring log n times, and each time you are just multiplying two things, mod n comma qx. What is the bit size? Bit size is degree of q times log n. So everything can be done in O tilde of that. Okay, so this is the time complexity. So in this much time you can compute x plus a to the n mod n comma q. If degree of q is small, this is polynomial time. Small means polynomial in log n. So this actually works. It gives a different and a new randomized primality test. So this idea gives the Agarwal-Biswas randomized primality test. So what it does is that just check x plus 1 to the n, is it the same as x plus x to the n plus 1 mod n comma qx for a random qx of degree around log n. So that is the low degree q. You can pick it randomly. It's a randomized test. If n passes it, you declare n is prime. If it doesn't pass, then obviously n is composite. Okay, so that's the new randomized primality test by Agarwal-Biswas. This is what we de-randomized. So we de-randomized it by studying x plus a to the n minus x plus n, x to the n plus a modulo n comma a very specific q which is cyclotomic polynomial. Okay, we use this. So again, two changes. One is we are using a, second is we are using specific q, not a random q. So let us first look at the test because it is so simple, and then look at the detailed proof. input as always is a number n in binary. So step 1 as always is if there exists AB, n is a to the b, n is a perfect power, then output composite. Otherwise, so the motivation for this second step will be clear later. It basically fixes the R, what R to use. Compute the smallest R such that the multiplicative order of n mod R is large. It's around quadratic. And then check for numbers 1 to R whether they factor in. Such that the GCD of an factors in, then obviously you are done. Now comes the bulk of the proof, bulk of this algorithm. It will check x plus a to the n identity for all the a's. Again, something unmotivated at this point, 2 square root r log n, these many a's. Let's call this L. So if the identity holds, if this identity holds, well, or the, let's say the opposite, if somewhere it fails, then that's a certificate, that's a proof that n is composite. If this fails, then output composite. And if you test for all these a's, it never failed, then you declare prime. That's the last step. Okay, so this is the algorithm. It's basically step 4, the identity being checked for many a's, but this number of a's depends on R. How big is R? Let us first do that. Let us first estimate that. So say for all R less than equal to big R, order of n mod R is at most 4 log square n. It never exceeded 4 log square n. Then so what does order of n mod R being small mean. It means that if you look at this product n minus 1 n square minus 1 dot dot n to the 4 log square n minus 1, this product is divisible by r. In fact, one of the factors is divisible by r, wherever whatever the order was. So for all the r's up to big R, there is this divisibility condition. Let us call this product pi. So this means that the LCM of all the numbers divides pi. How big is the LCM of numbers 1 to big R? So LCM of these numbers this is at least 2 raised to r. You can check this by distribution of primes. And how big is pi? Well, pi is a product of these numbers which are up to n to the 4 log square n. So this is at most n to the 16 log 4n, at least smaller than that. Okay. So which will mean that if the LCM divides it, then pi has to be bigger than this. So which means r has to be less than 16 log 5n. Right, so small r cannot exceed this. Okay, so this means that there is an r smaller than 16 log n 5 for which step 2 passes. So not everything from 1 to 16 log n to the 5 can fail in step 2. So you get a small r, and from that what you get is time complexity. So AKS test takes time. Number of times you will test is L times O tilde r log n square, because the degree of this modulus is r. So r log n square is the time for one test. So you get L times this. L again is around square root r log n, right? So this is O tilde r to the 1.5 times log n cube, and now you plug in log n to the 5 here, so you will get log n to the 10.5. Okay, so it's a very slow algorithm, but nevertheless it is polynomial time. Let us now analyze why the answer is always correct. There are no random bits involved. So first is simple observation that if n is prime, then AKS outputs prime. Well, because if you look at the algorithm, only place it can output composite is if n is a perfect power, which it is not. If n factors in step 3, which it will not, or in step 4 this congruence fails, which it will not, right. So the only possibility is prime. Okay. What happens when n is composite? That's the main challenge. So this will need some time to prove. Okay, that's the proof here is where all the techniques lie. The algorithm is designed so that this proof works. So let me state the idea in advance. The ideas involved are, obviously you do Chinese remainder theorem on Z mod n, but also on Z mod p. So Z mod, so remember that you are going modulo both n and x to the r minus 1. So you do Chinese remaindering on n, but you also do it on x to the r minus 1. Okay, double Chinese remaindering. And second very technical thing is, we will be working with two multiplicative groups. One I will call I, other I will call J. I will be group of numbers, J will be group of field elements. So these are the two groups which will help us finish the proof. So let us do that, see how this works. So for the sake of contradiction, it's a proof by contradiction. Suppose for a composite n, all congruences in step 4 pass. Okay, all the congruences hold. And let prime p be a factor. So now we will see what information can we deduce. So as promised, first we will look at multiplicative group I of numbers. What are these numbers? So I is defined as the group generated by n and p mod r. Okay, and note that the size of this group, well, since it contains n square, so what does it contain? It contains n to the I, p to the j mod r for all ij. right? That is what these are the elements of the group, n to the I, p to the j. So clearly it has at least as many elements as is the order of n. So the size of this group is at least order of n mod r, which by the algorithm is at least 4 log square n. Let me make a remark about why this group I is important. What is the significance of this? So note that step 4 implies that x plus a to the n to the I p raised to j is the same as x to the n to the I p raised to j plus a. Modulo p comma x to the r minus 1. So step 4 and the property that x plus a to the p is x to the p plus a mod p. Both these things, right? So step 4 means that x plus a to the n is x to the n plus a mod n comma, so p comma x to the r minus 1. Moreover, since we have this identity x plus a to the p equal to x to the p plus a mod p, you can now apply both. You can apply n in the exponent, you can apply p in the exponent, and you can actually keep deducing all these congruences for all ij. Okay, this motivates the definition of I. These are numbers of interest. Okay, next we do the subgroup or the group J. So let each be an irreducible factor mod p. Now define J to be the group generated by all these x plus a's that we tested for. Fine. So x plus 1, x plus 2, dot dot x plus l, multiply them as much as possible, and then take remainder modulo this ideal p comma h. This is a subgroup of the finite field. So fpx mod h is a field. Okay, so the second subgroup J is subgroup of this field except 0. Again, what is the rationale? So, note that step 4 implies that for all elements f in J, fx to the n is f of x to the n mod p comma h. Why is that? Well, because it is true for x plus 1 by step 4 congruence. What is step 4 congruence? It is this x plus a to the n, x plus 1 to the n congruent to x to the n plus a, x to the n plus 1 mod p comma h, right? P divides n, h divides x to the r minus 1. So, that congruence is true for f equal to x plus 1, it is true for x plus 2, but then you can also multiply these two, and then you get this congruence to be true for x plus 1 times x plus 2 and so on. You can multiply as many times as you like. So, this motivates J. So, both I and J are motivated, we have tested for them in the algorithm, and let us talk about now the size of J. I claim that this is at least 2 raised to L comma T. It's exponential in the number of tests you have done. It's actually at least n raised to 2 square root T. Why is that? Well, you just look at the number of subsets of 1 to L. So, number of subsets is 2 raised to L, right? So, that is what roughly you will get. Formally, what you do is consider two elements f comma g in J that are products of only T many x plus a's. Basically pick T or less x plus a's and then multiply them. Look at two such products for two different ways of picking. I claim that they are different. Suppose not. Suppose f and g are not different in the field. Then by the step 4 test, so fxm is g of xm. So, by step 4, you get fx to the m is equal to gx to the m, which is f of x to the m, and remember that all these x to the m's are different. So, this means that f of y minus g of y formal polynomial has size of I, that is T many distinct roots. in the finite field fpx mod hx. These many distinct roots are there for this polynomial fi minus gy. Well, but what is the degree of fi minus gy? It's less than t. Which could only mean that f and g is the same. So, if you multiply x plus a's in two different ways, t many x plus a's in two different ways, you get different products, which gives you a lower bound on the size of j. So, number of degree less than equal to t so this is at least 2 raised to min of L and T as claimed above. Okay. Well, this is not finished yet. We have to prove the second inequality also. So, this means that let us consider min of LT. So, min of LT is at least L is 2 square root r log n and T was shown to be, well, let us keep T for now. Remember that T is less than equal to R, because T was the size of the group mod R, right. So, this is min of 2 square root T log n comma T. What is the min of these two numbers, these two functions? Well, we have taken T to be more than 4 log square n, didn't we? Yes, T is at least 4 log square n. So, in that range, min will be the first function. So, you get 2 square root T log n, that is the min, which gives you the second inequality. So, you get that j is at least n raised to 2 square root T. Okay, so, we have shown these two lower bounds. We have shown that j is a large group of finite field elements, and we have shown that I is a large group of numbers. So, based on this, we will deduce the contradiction in the next class. Stop.